yeah, extremely interesting topics. And yeah, I cannot take too much credit for organizing this once again, because Anastasia, yeah, to be honest, is a little bit better at this than me. So I will, yeah, I hope you will enjoy the talk, and I think I might forget something if you have anything else.
Certainly no. So you said most of it. So yeah, welcome here at JetBrains again. We're happy to have you here back. Haven't seen you for a month, right? Good to have you back, really. So yeah, I just wanted to say a few things. First of all, we don't have planned speakers for the next year. Maybe that's someone here in the room. So if you want to speak at the meetup next year, it's a very good place. Again, I think I said that already previous time, but again, it's a very good place to train your talk for maybe some good conference next year. Who knows? Maybe you're like the big speaker for the next big C++ conference. Start here. That will be like a nice start with this very nice audience. And also we have some nice prizes, both from JetBrains and ThinkCell today to reward you for the best questions. So please be attentive to the talks, prepare your questions to the end, I guess. And in the end, we'll do some nice question sessions. And between the sessions, we'll have something about half an hour break to finish the pizza, drink, have some rest, and then go to the second talk. That's mostly it from me. Something else?
ThinkCell is sponsored the pizzas today, and also I wanted to, just in case not everybody knows, but there's two Anna and colleague, Julia, sorry, and well, Jonathan is also from ThinkCell, but I mean they're there to, if you're interested, stuff like that. So yeah, that's it probably for me. So I think we can start with the first talk. So Jonathan Müller, I would be cheating a little bit to say he does not need an introduction, and here he is, but that would be probably lazy. But yeah, the thing is, he's pretty well known, and he gives a lot of talks at conferences. Yeah, you have a very successful blog, it's fair to say. And the book I'm reading now also references your blog. It's
really?
The Klaus Engelberg.
Oh, yeah.
So probably you know him. But
yeah.
But yeah, so without further ado, let's hear it for Jonathan.
It's good to be here. It took me a while to get here because the Dutch train network had a partition and I was stuck in South Limburg for a while because the one train track was blocked for like 3 hours. So that wasn't nice. But I made it. So I work at ThinkCell. We are a company, we do a plugin for Microsoft PowerPoint. So it makes it easier to do data visualization, create slides. And we are hiring, in fact. So we're looking for the next C++ developers to grow our team. So if you want to work with me, we are like a bunch of really smart people. You can work with us in Berlin or also remotely. So I work remotely. We offer 130K after a year. I was told that I should say that. And we've got like a really great philosophy of like no scheduled meetings, no deadlines, no overtime. So you can just take a task, take your time, and implement it as much as you want. And I'm here to talk about what I'm doing. So I maintain the core library for ThinkCell. So think like Boost. It's sort of like an extension of the C++ standard library. It's used by our less than 30 full-time developers and as part of our 20-year-old mono repo. But it is continually updated. So we've got like a million lines of code or something that we continually keep updating to the latest standards. We always compile with the latest flags, use whatever features supported by our compilers. And because they're MSVC, they're a bit constrained in that regard. And with this library, we're sort of able to experiment and refactor a bit to try our techniques, experiment, see what works. It's open source. At that URL, part of it, more and more is getting open sourced over time. And as I mentioned, like it's sort of like an extension or complement of the C++ standard library. It's non-monolithic, so you can just plug and play individual parts. And crucially, we do not want to guarantee any backwards compatibility so that we can always create the latest and best stuff.
Yeah, sorry. You said MSVC, right?
Yeah, we write a plugin for Microsoft PowerPoint, so MSVC is our main compiler.
Did you try to compile it with ClankCL?
We are not, like, I want us to switch to ClankCL so bad, but we're not quite there yet because our build system isn't really a build system, and it's an entire thing. So, but yes, yeah. So the library sort of consists of 4 parts that I want to present. First of all, we've got a bunch of stuff that sort of improves C++. Then we've got like the small utility functions that are just one-liner implementations that make your code nicer. We've got our custom ranges, which is sort of like the main big feature of our library. And if finally we can look at strings. So as you know, C++ isn't perfect in many ways, and it sort of has like a bunch of stuff that you really want to work a bit differently. And we sort of use the library to change that. So for example, in C, there was a single cast operator, right? You can use it to truncate a float to an int. Or you can interpret an object as bytes. Or you can convert a pointer to an int. Or you can remove const. And there are sort of like 4 very distinct operations that all use the same syntax. Right? And C++ improved on that by introducing dedicated cast operators. So now you have to use like static cast or reinterpret cast or const cast. And note, for example, that now like the code that converts like the pointer to the int is really obvious that there's a potential bug because we are doing like a cast to the pointer correct integer type, and then we're doing another one to short, right? Which sort of stores away information. So this is good, right? This improves on C's single cast. Yeah, dynamic cast is also a thing, but yes, more cast operations. But let's just focus on static cast. And static cast on its own does a lot. So for example, you can use it to truncate over arithmetic types, like float to int, big integer to short integer, and so on. You can also use it to call a constructor or a conversion operator. So if you're a class, you can use static cast to convert between classes. You can convert a character type to another arithmetic type, including float. So you can convert the character A to a float using static cast, which is a weird operation. I'm not sure why you would want to do that, but static cast can do it. You can also convert, if you have an enum, you can convert it to another arithmetic type, and again, including a float. So you can convert pi. I don't know so the second float should be my enum, so you can convert pi to my enum. And then you can also do like unchecked casts in a class hierarchy. If you have a void pointer, you can also use static cast to convert it to a T star, or you convert an arbitrary pointer to void star. There are 2 more operations you can do with static cast. Can anybody tell me one of them?
Well, there is the CRTP. It's not exactly another thing, but in CRTP you can.
Yes, a CRTP is a base class cast. What? Non-void pointer? What do you mean by non-void pointer? You can use static cast to convert a void pointer to a T star. Oh, yes. You can't do that with static cast, but you can convert a void pointer to a static cast. You have to reinterpret it. Yes, correct. Okay, so one of the things static cast can also do is it can do a move, right? You can static cast to an R-value reference, and that's a move operation. And then finally, you can also use a static cast to cast a void. And this sort of like this throws away value. And those are like 9 different ways that are just, there should be dedicated cast operators for that, similar with the way C, because they are fundamentally distinct operations. Yes, you can also use maybe unused to discard. Yes. But then you have to create a variable and make it as maybe unused, but yes. So at things that we introduced explicit cast in our code base. And what explicit cast can do, it can convert a value to another using classes, if that conversion is safe. More on that later. You can convert between actual numbers, so ints but not chars, with a debug check against loss. So if you convert an int to a short and this will truncate, explicit cast will do like a runtime assertion that you shouldn't want to truncate there. You can convert between character types, and you can convert to bool, and that's it. This is sort of like the safe subset of static cast, the operations that are perfectly valid to do and not the weird stuff that you also might want to do. We also gave it the ability to create, to give it like multiple arguments. So you can have an explicit cast to a class, and this can essentially invoke a constructor. And it can also do aggregate initialization, and it can invoke a user-defined customization point. And we introduced that because we wanted to add constructors to standard library types, but we can't really do that, right? Because we can't add a new constructor to standard library, but we can customize explicit cast for standard library. So for example, in C++ 23, you will finally be able to convert like an arbitrary range to, for example, a vector of string using standardization 2. And this is be also possible in our library for like ages using explicit cast. So explicit cast provides us a way to add like more cast operations to classes that we don't really control. So for example, we can convert a range, we can explicit cast it to a vector of string. Explicit cast is constrained for like safe conversions. You cannot use explicit cast to do like base class slicing. You will not be able to have, for example, if you have like a temporary span or something, you cannot explicit cast it to another span, so then it would be dangling. You cannot create a reference to a temporary. And this is controlled by introducing new concepts, safely convertible to and safely constructible from. This is like the standard library type traits is constructible and is convertible, but they're constraints to be safe. And when they are safe, this isn't really something that we can automatically determine. So we've got like traits that you can specialize to mark something as unsafe. So if you've got, for example, the constructor from string view that takes a string, that is an unsafe conversion because it will not take ownership over the string, right? So we mark it as unsafe, and then explicit cast will not be able to do that. You would have to use another mechanism to get the safe conversion. Yes. Yeah, by default, we assume a conversion is safe and you have to opt out. Because in practice, like, it would be safer to do the other way around, that you have to opt in. But I guess, like empirically, the most stuff is safe. So if you, right? Yeah.
So how is that, like, for example, differentiating between like converting construction, like calling the conversion, because there's a lot of different ways that you can convert things.
Yes.
But like when you say, like you have safely constructible from, like a single argument, that just
yeah, so safely constructible from checks, it does like the built-in stuff. For example, so it has some rules, for example, an int is not safely constructible to a short. But if you have like a class, and then safely constructible from by default is just like is constructible from, and then unless the class has specialized a trait to opt out of that. So that is the way that works. And so we've got explicit cast to cover like the majority of cases for static cast, and then for everything else. So explicit cast in our code base is the cast that we pick by default, unlike not static cast, explicit cast. And then for everything else, we've got dedicated cast operators. So for example, if you want to do a signed unsigned conversion, you can use as unsigned and as signed. If you've got an enum converted to an integer, you can use to underlying and from underlying. And this will not convert an enum to a float, for example. For cast in the class hierarchy, you can use base cast and derived cast, and this does like dynamic cast with a debugger assertion and static cast in release. If we want to convert a void pointer to anything else, we use void cast to really indicate that we want to cast pointers here. And then the static cast to void, we use TC discard for that, which is just a more expressive way of doing it. So one downside of explicit cast is if you've got like a function that returns as some very, very long and annoying type, and then you have to use the explicit cast in multiple places, which is a bit annoying. So we've got return cast for that, which sort of like does the magic automatically. It will convert it to the correct return type. And the implementation in principle would be quite simple. So for example, we just need to have a function that takes our source, and then it returns the return cast impl. And the return cast impl has a templated conversion operator. This is appropriately constrained in the real code. This will then convert it to the thing. And so if you, for example, write return cast of a float, and then you return a char, this will create the return cast impl. And this will then invoke the templated conversion operator of char. In the real code, this wouldn't compile because char is not like, shouldn't be convertible from a float. But there's the cause the conversion operator and does the conversion. So this is nice, unless of course you use auto, and then suddenly the function returns a return cast impl, right? Because it doesn't know what to cast to. And we want to prevent that. And this is what gets a bit more annoying, because so we want to prevent returning from function. So we just delete the copy operation, right? And then we can no longer copy it and cannot return from function. So decal type auto, this would be a temporary. This would also work, but what's the problem with? Yeah, we've got return value optimization, or rather, more precisely, we've got like copy elision in C++17. So in C++17, this will just compile fine, because the compiler no longer needs to invoke the copy constructor to return something from the function. So even though the type is not copyable, we're able to return it. And this is because we're returning a temporary. Yeah. So if we return a temporary object, we don't need the copy constructor.
Well, you have a difference between like implicit move and the copy leaf. That's PR value or PR value.
Yes. So this is a PR value, so we will have copy elision. So to prevent copy elision, we must not have it into a PR value, we need an X value. So if it's already like an R value reference, then to perform the copy, we will invoke the copy operation. And so what we can do for that is we create an X, like this is technical terms, so we create an X value and not a PR value by using the following. So we want to cast it to a return cast impl const R value reference. We do that by overloading the uni operator plus. Because then when we write plus return cast, this will create a const R value reference. You're following me? And because we have a const R value reference, you no longer have a PR value, copy elision doesn't apply, and the compiler will complain that we're attempting to invoke the copy operator. So we just need to remember to write plus return cast and not just return cast. If you write just return cast, you will do the wrong thing, so you need to write plus return cast. Right? Of course, this isn't really feasible to because we need to, if you remember to write plus, you can also then just fix the auto, right? We want to catch implicit misuse. So we use a macro. TC return cast is a macro that does like plus and then creates the object. And that way, this will not compile, right? Because we have an X value, we will not invoke the copy constructor. And this is the sort of thing I do all day. So, and I know what you're thinking, right? Macros are evil. Well, the thing is, almost every macro demonstrates a flaw in the programming language, in the program, or in the program. Janis Tostov says that. And this is a flaw in the programming language. But we want to prevent auto with a particular type. And the only way we do that, the only way I figured out to do that, I didn't write it, but the only way we figured out to do it is to use the macro with the thing, and so we have to use a macro. And we use macros a lot for that sort of thing in the library. And so we've got a bunch of macros to sort of work around minor flaws in the programming language. For example, we've got temporary lifetime extension. So this is a function getStrings. GetStrings returns a vector of string. And then we can use that. So even though getStrings returns a temporary, we're able to bind it to a const reference. And this will work fine because the const reference, we've got temporary lifetime extension. Whenever we bind a reference to a temporary, the temporary will live as long as the reference. So this is perfectly valid. However, this one isn't, because we're no longer binding a reference to a temporary due to the way the operator works. So lifetime when bound to a reference, but here we're binding it to the result of the call operator, and that one is already a reference, not a temporary. So we're just copying a reference, and temporary lifetime extension doesn't kick in. We've got a reference to the first element of the temporary, and then the temporary gets destroyed, and we just have a reference. And
Did you try not writing this kind of code?
yeah, I get that. The other problem with temporary lifetime extension is you have decal type auto. So this function, the first line is fine. We create a const reference to the thing, temporary gets extended as long as the reference is. And then we are able to use that throughout the rest of the function. That's fine. But then when we return it, when a function that returns decal type auto, the type of strings is like an auto const reference. And so this function will return an auto const reference to the temporary. But again, when we return it, we return like a copy of the reference. So the original temporary gets destroyed, and we're just returning a dangling reference here. So yes, we tried not writing this code, right? Do not use temporary lifetime extension. It's nice in the specific situation where it works, but in most cases it doesn't work, so you shouldn't use it. So we can always use autoconst. It's the more safer way. But then when we always use autoconst, then here we're creating an unnecessary copy. Because this function, like return, already gives us the const reference. And then we're copying it, even though we shouldn't, because presumably it lives long enough, right? So then we need to have a more nuanced guideline to say autoconst ref, but only if it's safe, otherwise autoconst. So the actual guideline is if we have a function that returns an L value reference, we can safely bind it to an autoconst ref. But if it returns by value, or it returns an R value reference, then we need to use autoconst. And we automated that guideline using a macro. So we've got tc auto cref. When calling with getStrings, this returns a value, so it will be autoconst. When we're calling it with get strings from somewhere else, this already returns an L value reference. So this will be an autoconstref. And when we call it here, this still gives us an L value reference. So this will still be an L value. So that hasn't really helped us anything. Because in that case, like we're still having a constref to the temporary that's already destroyed. So this requires more work. We sort of need to have the correct signature for everything. So what we really wanted is like an additional overload for like vector that takes on, if you call it an R value, then we want to return an R value and not an L value reference, so auto-cref works. So we need want the API to be correctly reflect the lifetime of the things for that to work. So we don't actually use the index operator, we use like tc_add, which is like our own function that does the correct logic. But that's the sort of idea. So we spent a lot of time trying to work on both the C++ language and like C++ APIs, because we want to write like the most performant code while keeping it simple. But then like we frequently find this sort of holes in the C++ API. Function pointers. Function pointers aren't that great either. So for example, when you've got an overload set, you cannot create the address of the function because the compiler doesn't know whether we want the first one or the second one. Then we've got code like this. What's wrong with this code? All of begin end is lower. Yeah, so depending on which headers you've included, there can be multiple overloads of is lower. But the main issue is that we are essentially not allowed to take the address of a standard library function. Because the standard reserves the right to add more overloads in the future. So you're not allowed to take the address of anything your code may break. And we don't, like the C++ committee doesn't want people yelling at them for breaking the code, so they just banned it. So yeah. Yes?
So you say we're not allowed to write code like that?
Yeah, we're not allowed to write code like that.
Does it mean that it's undefined behavior? Or that it may compile and it will not work?
So it is undefined behavior, but it's like library undefined behavior. And it's not like the compiler will start optimizing based on that. It's just like the standard library doesn't allow you to do it. Sort of the weaker form of undefined behavior. Where it's just like crossing, like going up the street when the traffic light is red. Right? That sort of undefined behavior, not the one where you. Anyways. And then also like, if you've got like map and we want to give it a custom function pointer, this is just wasteful because now the map needs to store an additional function pointer. Right? This is 8 additional bytes to there, even though the information is statically available. So we ban function pointers, and instead we use lambdas, because lambdas don't have any of these properties, these problems, and we use a convenient macro to create the lambda. So this macro takes the name of a function and sort of creates a lambda that calls that function. And then we don't have any of the problems because we can use the macro with an overload set, because it's just the name, and then when we call it in the lambda, we can have a thing that represents the entire overload set. You can use it with standard library functions because we're not taking the address, we're immediately calling it. And when we use it with std_map, this is an empty lambda, like it doesn't capture anything, so we're not storing any additional bytes. Similar thing happens with member pointers. Here the issue is that member pointers require this weird syntax to call them. So if you've got a pointer to member, then you have to use like the dot star or arrow star operator to call it, which is a bit annoying. And so we've got more macros for those, tcmember and tcmemfun. And they take the name of a thing using the access that we want and then wrap it in a lambda. So for example, we can say get size, which is a memfun that just calls dot size on whatever is the thing. And then we can call get size with both string and vector, for example. And this just creates the lambda that calls the appropriate thing. And they're like really convenient if you just want to do sort of like a projection in an algorithm. For example, you want to sort based on dot first name or something, and then you can give you a tcmember dot first name. We've also got tcinvoke, which is like std invoke, but because we don't use function pointers or member pointers, we don't need to worry about them, so we just ban them in there. And instead, we sort of do an automatic expansion of tuple-like objects. So what this means is then we've got a function that takes 2 arguments. You can use tcinvoke to give the 2 arguments, or it can give you a pair, or tuple, or an array, and it will just automatically unwrap them. This is really convenient. For example, we want to, when we go to ranges, we want to zip to ranges, and we want to do something with like one element from each, and then we can just use for each zip. Even though zip gives us a tuple, we can just unwrap it conveniently in the lambda, because internally it uses tcinvoke. And this morning I'm actually working on making tcinvoke even better by sort of telling you when, so for example, when you want to call a function and you're giving some arguments, and then you want to, for example, min. A min is a function that takes a bunch of references, and then it returns a reference to the smallest one. But if you're calling min with temporaries, you don't want to return a reference to a temporary. You want to keep it as a temporary. So what I'm currently working on is giving sort of differentiating TC invoke. So min can tell whether an argument was a temporary or an actual reference that lives long enough, and then sort of pass that information through. So I'm working on a bunch of stuff on there currently. So that's quite cool. So the second part is we've got like small utilities to write more fluent code. For example, the standard library has std exchange. Std exchange takes a variable and a value and sort of updates the variable to the new value, and it returns the old one. And that one, we love it. So for example, here we've got a move constructor for a smart pointer that wants to copy it over and sets the other one to null. And this can be a one-liner using std exchange. So we want to exchange pointer to null pointer and return the old value. And we sort of love the function, we use it all the time. We've got something similar, TC change. For example, we've got a custom optional to have optional references. And the destroy function, if it has a value, we want to set it to false. And then we want to call the destructor. And for that, we use TC change. So TC change takes a variable and a value, and it updates it, and returns whether we did an update. So if we were able to change has value to false, then we want to call the destructor. And we sort of, again, use this one-liner in a bunch of places. For example, we often have code like this. So we want to do something. If it's dirty, we want to clean it. And writing it like that in that order, so we first reset dirty to false, and then we call clean. This is problematic if clean throws. So if clean throws, we've already set dirty to false, and then we will are in an invalid state. However, it is safe if clean calls true again. So if recursively clean calls true again, then we've already reset the flag, and we're not stuck in an infinite loop where we just keep clean. And because we're writing a PowerPoint plugin, we're dealing with a bunch of GUI events, right? And when we change something, we may trigger the same GUI event recursively, so we need to be really careful about this sort of thing. So this is why we write dirty is false always first, and this is the way TC change works as well, to sort of guard against reentries. Of course, if we were to write it the other way, then we've got like the exception safety problem no more, because now if clean those, we haven't reset the flag, but we've got the reentrance problem. However, TC change and another try catch, we can sort of get both, right? So we want to change it immediately, but then need to reset it after an exception. And this is sort of, in the case, then we want to do both. This is sort of the pattern, which is annoying. So we've got like more utility functions to have like an on exception, do a reset, that sort of thing. And change is actually more general. So the primitive is assigned better, which takes like a predicate, a variable, and a value. And if the value is better than the current value, then we update it and return true. And in change, better is just the value is not the same, but we've also got assign max and assign min to like update something to convenience. So if you want to do an operation where you want to frequently determine the maximum, something of a range, assign max and assign min are quite useful. So we've got functions that modify things, and they can be written in two ways. As a transformation, where we take a value, modify it, and return the modified value, or as an action where we take a reference and then modify it in place. And they're sort of isomorphic. For example, you can write a function modify that takes a reference and a transformation and turns a transformation into an action by just applying the function and modifying it in place. And modified, which takes an action and turns it into a transformation by taking a copy, modifying the copy, and returning the copy. And we can optimize modified by checking. So if we've got like an L value, an R value reference, for example, we can modify it in place because the caller doesn't care about the old value, so we can save the copy. So like in principle, from a mathematical standpoint, it doesn't matter whether we write everything as transformation or as an action, because they're both equally powerful. But actions are more efficient because we're able to modify them in place, right? We don't need to create a copy with a transformation. So at Thinkcell, we only want to divide actions. So we would write a function sort that takes a container by reference and modifies it in place, and not a function sorted that takes a container and returns a sorted copy, right? Because that one would be more efficient, less efficient. Similarly, we want to call the increment operation of the iterator, which is an action that modifies in place, and not the next function, which creates like a copy and returns an incremented copy. And so to sort of turn an action into a transformation, we've got a macro, TC modified, takes an object, and an operation that we want to do. And then we can sort of give it, like, for example, we want to say a container, call sort on the container, and this will then create a copy that called sort. Or next, instead of stood next, we use TC modified iter and then the increment operation. And that way we can just write the actions and transparently convert them into transformations. We've also got a bunch of code like that. So we want to compute a result which returns an optional. And if the optional was successful, then we want to get the result. Otherwise, we want to compute some fallback. Now, stood optional has a function value or, which does that sort of logic. But the problem is it will always compute fallback, even though the value might already be there. So we want to only lazily compute fallback only if it's really necessary. And for that, we can use TC lazy. And TC lazy will sort of do lazy computation of the argument. And the way it works, so you have to look at the implementation of value or. So value or checks whether we have a value, and if so, return it. Otherwise, we return the fallback. And note that it takes anything. The fallback can be anything. And then when it returns, it triggers a conversion to T. And this is the idea behind TC lazy. So it's just some lambda, and then it is convertible to whatever that lambda returns. And when you trigger that conversion, you will invoke the lambda to do the conversion. And then it's just another macro that creates the type, wraps everything in a lambda. For more details, I've also written a blog post about it. And this is sort of the idea. Because now we wrap the expression in a lambda. The lambda will only be evaluated once we trigger a conversion. So we will lazily compute the value only when necessary. Since C++23 optional, so this is the code we write, but since C++23, we can use .or else on optional, which sort of takes the function directly. Yes?
Like before, you make use of inheriting from a lambda, right?
Yes. Yes. Yeah. Yeah.
When is it produced?
I think you can always inherit from a lambda.
Is it already from the first?
Yeah, because a lambda is just a class.
Okay, so C++11 is a lot.
Yeah. Lambda is just a class. It's not final, and there's no way to make it final. So always able to inherit from the lambda. You just need, the annoying thing C++11 is you need to figure out the type of the lambda in order to pass it. And so you need like a template because you can't do Deckel type, right? But yes. Yeah, so it added or else, which sort of takes a lambda directly, and so you don't really need a TC lazy. So in C++23, like it's part of the monadic operation. So we've already seen value or takes a fallback, returns the value or the fallback. And the fallback is something that's convertible to T. Then there's or else, which takes a function. And when the value isn't there, it calls the function to get the value. Then there's and then. So this takes the function, and it will invoke the function on the value and return the result, or it returns a null opt. And here the function already returns an optional of a different type. So it will either return the function called with the value or null opt of that function return type. And similarly, we've got like transform, but here the function returns a value and not optional. And so in transform case, we will wrap the result in optional. And these are sort of like monadic operations that are really useful when dealing with optionals. For example, you've got an optional string, you want to transform it to an optional int, and so on. And so they only added to optional and then later to expected. But for example, they could also be added to like a pointer, right? Because a pointer can also have a value or not. And then you also want to do this sort of operations. So at ThinkCell, we have them as non-member operations. So we've got TC value or, which takes anything which is like an optional and sort of at the same logic. It calls star opt or returns the fallback. We don't have or else because this is just value or, and then we give TC lazy. So we don't need or else when we have TC lazy. We can just wrap the expression in TC lazy. Then we've got and then is exactly the same. So it either returns the function called with the value or whatever is the default constructed version of that optional. And then we don't have transform because transform is really like we want to take the function and we want to return it into a function that returns an optional. So we sort of chain a function into one that returns make optional. And this is a bit verbose, but in practice, the function is almost always a lambda that you're writing inline. And then you might as well just give it something that returns the lambda and optional directly. You don't need to modify an existing one. And this makes it convenient to write code like that. So here we want to take a user ID and want to unsubscribe from the mailing list. So we first need to look up the user. This can fail, so we need to check whether we actually have a user. And if so, we want to get the email. Otherwise, we want to get an empty optional. And then if you have an email, we want to remove that email address from the subscriber list. And if that did something, then we want to like cache something in a database or do something to handle the new subscriber list. And this can be really conveniently written with and then, because it actually takes multiple functions and will chain them. So we say lookup user, and then give me the email address of that user. And then we move from the subscriber list. And finally, this returns a bool, and we sort of treat the bool like an optional void. So it isn't optional, but it doesn't have any associated data. And this will mean that the final function is invoked with the value, but there is no value, so it will just invoke with no arguments, and it will change the subscriber list. This is a sort of, we prefer this sort of declarative style of writing this function. We just don't need to worry about the ifs and so on. We just do the operation that we want to do. This brings me to the core of our library, which is the ranges. So C++23 added ranges to the C++20 added them to the standard library. So this is code that prints some squared integers that are even. So we take a range of all integers between 1 and 20, then we filter the ones that are even, and then we transform them by replacing each element with the square. And this is valid C++20 code that you can use. So at ThinkCell, our library predates ranges and also ranges v3. So we've got our custom ranges, and with our ranges, it looks like so. So we don't have a pipe operator, so just call a function filter, give it a range and lambda instead of using the pipe. But otherwise, it's the same. So just get a range of squared integers, and then you can print them. And we use TC for each instead of the range-based for loop. More for a reason, I'll get to that. And so, but what's the difference between the standard library ranges and our ranges? And for that, we need to look at what exactly is a range. So in the standard, range is something that has begin and end, returns iterators, and then you take over them, and that's it. But we've added two more kinds of ranges, generator ranges and index ranges. And they are really useful. So, for example, this is an example from Ag Niebler, when ranges were standardized, about a function that generates all Pythagorean triples. So it will return all pairs of triples of integers x, y, z, where x squared times y plus y squared equals z squared. And this can be written using ranges like so. It just uses standard library functions and then this yield if. And this isn't really very obvious code to write sort of a range that gives us, this is an infinite range that will return Pythagorean triples, but it's not really obvious to us. And this is because of the sort of disjoint between external versus internal iteration. So with the iterator model, we're having external iteration. We've got somebody else that controls the iteration. We've got an iterator, and then the caller asks the iterator to get me the next element. This means that if the iterator needs to maintain state, like nested internal loops, we sort of need to construct a state machine that maintains the state, and this is a bit annoying to write with the iterator. It's much easier using internal iteration, where the algorithm is in control, and it will just give us the next value on its own, but the caller has no control over it. And then the iterator can just be a loop. And this is also the idea behind coroutines, where you can, with coroutine generators, you can just write internal iteration, but have the control of external iteration. So, for example, this is the Pythagorean triples using coroutines. You just write the 3 loops, check the condition, and then yield the value. And this is much nicer to write, and the generator will still give us iterators. So we've got sort of the best of both worlds here. We just got we've got the convenience for the caller with iterators, and then the implementation is pretty convenient, pretty straightforward. However, coroutines require heap allocation to store state. They're a bit opaque for the optimizer to do, because it's sort of we get the compiler to write a state machine for us. And then the optimizer needs to see through all that and optimize it out. And it's sort of, they're viral, right? Once you have a coroutine somewhere in the call stack, you need to have coroutines all the way through. So you can't call the inner thing. If you want to expect the if into a separate function, that also has to be a coroutine. And then we sort of need to yield values through there. So there's a bit of a downside. So things are we're using generator ranges. And a generator range is just a function that takes a sync, which is another function. And then we invoke the sync with each value that we want to return. And then we use a macro to allow early return. But basically, it almost looks like a coroutine. So instead of having a generator, we return a lambda that takes a sync. And then we invoke the sync with the values and just use this weird macro. And then on the call side, we can call for each. And what for each does is sort of takes the lambda that for each takes, so we wanted triples, and it passes in as the sync to the generator range. And then the generator range will invoke a lambda for each element, and we can point them out. And this doesn't require any heap allocation. It doesn't create any state machine. We just need to, the downside is we can't use the range-based for loop. We have to use for each, because we need to have a lambda that we pass that. And we also allow early return by returning either TC break or TC continue from the lambda. And then the return of break macro, so it just checks whether the expression returns TC break, and if so, it will forward the TC break by returning that from the function. And that way we sort of get like generator ranges with early return. And there are a bunch of optimizations to handle cases like functions that always return void, so they will never break, so we won't generate any ifs in those cases, but wouldn't fit on the slide. And generator ranges, so we can convert any iterator range to a generator range by just writing a lambda that takes the range, uses the range-based for loop to iterate over it, and call the sync on each element. But we can't do the other way around, right? Because we are stuck with internal iteration. So sort of generator ranges are more fun, like less powerful version of iterators, but they can be a bit faster and more convenient to write. So when we've got adapters like filter and transform, they provide both the generator range interface and the iterator interface. And then it prefers to call the generator interface because that's usually more efficient. For example, I can show you an entire implementation of filter using generator ranges because it's really trivial. We just write a loop, and we only forward it to the actual sync when the predicate is true. Right? The implementation using iterators is a lot more complex because the increment operator needs to skip call increment over the fundamental underlying ones until it finds one that fits the predicate. But like with generator ranges, it's easy, right? Just only forward the values where the predicate is true. And what's also really easy is like concat. So if you want to have a concat of multiple ranges, well, we just need to call for each on each one in sequence, and this is done by using like a for each and a tuple. So for each is a bit special, but like fundamentally, like if it takes 3 ranges A, B, C, we just call for each A, for each B, for each C. And like concat in C++23 as a range is really annoying because we've got like iterators that are variants of the underlying iterators, and then increments forwards to the active one, and then switches it, and it's like really complicated. But for generator ranges, it's easy. Just write 3 for loops if you want to concat 3 ranges. So the second kind of range are index ranges. So this is an iterator range. So we've got begin and end. Begin returns an iterator, and the iterator has a star, it has an increment, and it has a comparison with the end. And the iterator stores the entire state, so it needs to remember the current position, and it has a logic. So we ask the iterator, give me the value, go to the next element. Are you done? And with index ranges, which is something we've introduced, we've got just an index. And an index only stores state. So it only stores the position. And then the logic is part of the range. So you ask the range, given this index, what's the value that's stored there? Given this index, give me the next index. Given this index, are you done? And again, they are like 2 isomorphic. We can convert any index range to an iterator range, but just writing an iterator that stores both the pointer to the range and an index. And we can convert any iterator to an index range by just forwarding to the operation on the iterator. So we don't lose anything by using one or the other. But index ranges are superior to the iterator design for multiple reasons. For example, iterators can dangle. If you have an iterator to a vector and the vector is destroyed, you can still dereference the iterator. And then it will give you a value that's already destroyed. But if you have an index, you can't dereference the index on its own. You need the original container to index it, right? So when you have an index, they can't dangle. And even if they were dangled, like they're useless. You can't do anything with them once they're dangled. So they're much safer in that regard. Similarly, indices are less likely to be invalidated. So if you've got an iterator, which is a pointer into a vector, right, that can be invalidated when the vector reallocates. But if you just got the index, then this one will not invalidate just because you add new elements at the end. We can do very efficient bounds checking using indices because we've got the entire container. You cannot ask an iterator, hey, on its own, like the dereference operator on an iterator can't do a precondition, I'm a valid iterator, because it also needs to know the end. And it doesn't have that information. But the dereference index operation, it has the entire container. It can do the bounds checking. There's a bit of an esoteric point, but like they're more space efficient when nesting adapters. So, for example, this is a filter using iterators. And the iterator needs to store a pointer to the view to get the predicate, and then the current iterator. And it needs the pointer because in increment, it needs to access the predicate. And the predicate is part of the range. So we store an iterator and a pointer. But with index ranges, well, we just store the index of the underlying range. So we don't need to add additional data because we call the operation on the range, and the range already has the predicate. So we don't need to store a pointer in the index. So this means that if we, for example, got a filter of a filter of a filter of an input, the view needs to store the input and then 3 copies of the predicate. And then the iterator stores the underlying iterator of the input and then 3 pointers to each level of filter view. So the iterator is like really big. But if we're using indices, we still use the range is still the same size, but the index just stores the index of the underlying input. Right? So the index is the same thing. And then when we want to turn it into an iterator, we just need to store 1 pointer to the range and the index. And we don't need all these intermediate levels. So they're more space efficient because we don't need to add any additional data to the index in most cases because all the data is on the range. So we don't need to modify the index. So the standard library also has the concept of output iterators. And output iterators are iterators that are write only. So for example, we want to copy a back to a pointer. We can call ranges copy, give it the input range, and then an output iterator, which in this case is just a pointer. And this will essentially boil down to memcopy. It can very efficiently detect that it is a raw pointer, calls memcopy. However, if we're having a deck is not continuous, so it has to do a copy element by element. So it copies the first one to the pointer, then increments the pointer. It copies the next one to the pointer, increments the pointer. And this is a bit wasteful because like the deck is essentially a linked list of arrays. And each individual array is contiguous. So it could call like memcopy first array, go to the next array, memcopy that, memcopy that. But because of the output iterator abstraction, it's not really possible. Well, I mean, the standard library knows all those types and can do the optimization, but in general, it's not easy to do. And if we have a back inserter, which calls pushback on a vector, then we will call pushback for each element instead of the dot insert at the end, the entire range, which would be an option. But again, this is like difficult to detect in the generic case that we want to insert something at the end. So instead of output iterators, we're having appenders. And appenders have 2 functions. We can give it a single element, and it will append that single element. We can give it a range. And then we will append that entire range. And this gives us the opportunity to append multiple ranges at once. And so when we call tc append container, and then we give it a bunch of ranges, it will ask the container, hey, container, please give me an appender. And then it will use that appender from the container to append the ranges in there. And for example, when we want to, for example, one of the ranges is a deck, we can detect that and split it automatically into contiguous chunks and calling memcopy into the optimization. And as a bonus, we will also do some sort of explicit cast in there. So if you've got, like, for example, want to convert a container as a vector of strings and we're giving a bunch of string views, it will just work out and do the appropriate conversion. And all of this is powered by TC for each. So TC for each is sort of the fundamental algorithm that we use. It takes a range and a sink, and it will do a bunch of stuff in order. So it will check whether we've got an appender, and then we'll call chunk. We can customize for each. And then in order, it will prefer generator ranges, because generator ranges are usually more efficient. They're just a single loop. Then it will do index ranges, because index ranges have like the additional, like there's indices are smaller and so on. And if that didn't work, then we call iterators. So things that we do not actually use the range-based for loop, ever. Like it's banned in our code base. And this is sort of like the philosophical reason is that, like, if you've just got a simple, like, we want to use algorithms instead. And even if you just have like a very simple range-based for loop, like over time it tends to grow into an algorithm. Like you just add another if, and then you do a nested loop, and then you've got like this really big loop. So if you just ban it entirely, like we will always be forced to use algorithms. And then the second one is like we've got a bunch of generator ranges, because generator ranges are really convenient to write. Like you can very easily write a generator range that like reads entries from a database. But this would be very annoying to turn that into an iterator to work with the range-based for loop. And so we just have to use for each in many of cases. So we don't use the range-based for loop, we just use TC for each, which will handle generator ranges very convenient. So we've also got a bunch of more algorithms. Similar to the standard library, we've got like filter in place, which is sort of like predates the erase, is the erase remove if idiom. It predates the std erase functions that are now in the standard library. We've got functions like take first in place, which truncate a container. We've got sort unique in place, which is like a sort and then a unique, but it's more optimized, and like a bunch of your algorithms like that. And then, for example, we've got this concept of range returns. So for example, find gives us an iterator to the element it founds or an iterator to add. But maybe you just want the value in an optional. So you can, or you want to return bool, whether you found something. And then we can use these range returns, and they sort of control the result of the algorithms. So for example, you can use DC return value or none, and this will then means that find returns an optional of the value. A return bool means you return a bool. A return element index or none gives you like an optional size D. Take before or all gives you like a subrange of begin until the position that you found. Or like a subrange of anything, and like there are a couple dozen of range returns, so you can directly give us the information that you want, which is really convenient. Yeah. So finally, I want to look at strings. So we've been dealing with a bunch of strings in our code base. Yeah.
Question about your sync version algorithm.
Yeah.
What is those for power execution like
yeah, so we do not have parallel algorithms like that in the standard library, simply because the way our code base is structured, like we haven't really much use of parallel code the way, because we're like integrating into GUI application, and we don't do a lot of work in each cycle, so we didn't have a need to do any parallel work. Yeah.
So in your algorithm, you use a vendor instead of like a back element.
Yeah.
You say you need for optimization, but like is it significant, or is it like the optimization that so you use no copy instead of allowing compiler? Do you have like any numbers, or do you have like estimates on how this actually improves the performance?
Yeah, so I don't have any numbers, but like it sort of depends on what you're doing, but. Yeah, so this predates predates me in the company. It was already there when I joined, but it's also like even it's not gonna make it slower to have that interface, right? And like and optimizations are fun to do, you know. Yeah, it also has like. The appender interface, there are like standard proposals, like well, it isn't a proposal, but like people want to add something like that to the standard library, but also because of safety reasons. And because an output generator is just a pointer, you give it a fixed size buffer, it can overflow. But if you have an appender, which is more high level, again, it can do like bounce checking internally, and that's also.
Your experience with the compile time performance.
Yeah, so the experience with the compile time performance is we've got pretty good computers.
There are the error messages.
Yeah.
How big are your screens?
Yeah. Yeah, big screens, big computers. Yes. Yes. That's the trade-off you're making. Yeah. Yeah. We can discuss at the end. We have time for that. So strings. We're dealing with a bunch of strings, and philosophy is quite simple. Strings are just ranges. So we don't have specific strings functions. We don't have specific string types. We just use ranges, because strings are just ranges of characters. So we need to deal with 3 encodings. We use UTF-8 by default internally, but we do a bunch of interactions with the Win API and the advanced UTF-16. And then we've got like many ASCII string literals. And like in a perfect world, we would use char80 for UTF-8, char16t for UTF-16, and char for ASCII. The issue with that is this, like char80 is like 3 years old. So most of the code uses char for UTF-8 and not char80. So it's sort of like not really useful, because it's a different type than what anybody else expects. So we're using char for UTF-8, char16 for UTF-16, but the Win API takes white-char-t, so we have to use white-char-t on Windows. So we've got like a conditional thing there going on. But what do we use for ASCII? We want a distinct type for ASCII. 7-bit. 7-bit. Yeah, yeah. for like 7-bit ASCII. And we use a strong type for that. So we say like char ASCII is like a char restricted between 0 and 7F. And this is both like document intent of the API, and it also now allows optimizations. So if you've got like the Unicode transversion functions from UTF-8 to UTF-16, if you give it a string of char ASCII, it knows it can just do a static cast of each individual thing. So it saves a lot of work there. And we've got like most string literals are char ASCII in our code base. So we can save on transcoding them. Yeah, so this is essentially a bounded integer. It's more precisely like a bounded enum. So it doesn't do like arithmetic operations. But yeah. And then, so if we want to use just like strings as ranges, we've got an issue. What is range's size of ABC? Correct, it's 4. This is because a string literal is a char array, which includes a null terminator. So if you use a string literal as a range, you will always have this extra null terminator in there. We also don't have any distinction between like this is a string literal and this is a char array, which might be useful because we know, for example, that it's always safe to convert something like to create a string view from string literal is safe, but to convert a string view from a char array is not safe because it could dangle, right? So we lose that. And also the value is no longer statically known, which means that we cannot do like concatenation of multiple string literals to get like a big string literal that contains both of them. We would need to create like a temporary array and copy them over. And so this was one of the first projects that I wanted to do in our code base, is to introduce like a user-defined literal that takes the string and sort of encodes it in the type system. So if you write like ABC underscore TC, this will give you like a string ABC. And then you've got this noun and the type system. We can give it correct begin and end, and we can do like a bunch of compile time concatenations. And then we can also like determine the character type based on the encoding. But for example, we can say that U8, even though this would normally be a char 80, we can return a char because this is the type that we use for UTF-8. And then if you don't do any prefix, we can just say this is a char ASCII. And this is really useful because there is no like literal syntax to create like our custom char ASCII, so we can use that. This isn't fully integrated in the code base because, as it turns out, the compiler doesn't really like it if you turn every string literal into a distinct type. So it ran out of RAM, and I have 1 terabyte of RAM. So that was a bit concerning. So we're looking at ways on mitigating that, but like this is eventually what we wanted to do. And
what is EC? Is the EC just like holding a pointer?
And no, it does not. So this is an empty type, and like the entire string is stored in like the template literal. And when you call begin, it will instantiate like a char array with the correct copies. So, but yeah, like this is not fully integrated, so I need to handle a couple of issues on that. And it's also like because it's integrated in the type, we've got like optimizations like append. It can do loop unrolling and like append each literal statically instead of looping over it. That sort of thing. So like in principle, it would be very nice, but in reality, we need more RAM before we can deploy that. Yeah, so like minimum, like the library is modular. Like you can just call explicit cast, and this doesn't take any RAM. Like you don't need. But like the issue is that like it's also like the library also compiles fine. It's that the translation units that other people use, where they've got like 10,000 lines that use like, you know. So it's not really my fault, but say it's there. Yeah.
Do you interact with like a ASCII API that expects like null terminations? I feel like you don't include null, so you can lose this part from. Like,
yeah. So when we want to call a function that takes a null terminated string, end of string literal doesn't include the null terminator, but the null terminator is still there. So we know that fundamentally it is a null terminated string. So we've got for that we've got a function. I don't know. I might talk about it. The function makes string that takes a string and returns like a null terminated string. And if it's already null terminated, this is a now up. Otherwise, it will do a copy into the thing, and then if you can optimize it based on that. So, fun fact about std string: when you've got like the string can store UTF-8, like that's perfectly fine. And then the comparison, LHS less than RHS, because char is signed on Windows, for example, a non-ASCII char is negative. But even though it's negative, it is defined to do the unsigned comparison. So this assertion passes because A is less than, like A is 65 or something, and C3 is bigger, so this assertion passes. But if you were to use a vector of char, now the assertion no longer passes because then char is actually signed and we're doing a signed comparison. And this is a bit annoying because we just want to treat ranges, like strings, as ranges of characters. And then depending on which sort of type the range is stored in, we've got like different orderings. So we don't actually use string, we use like sort of string and then with the correct char traits. So if you're having like the same char, then we use the correct comparison, which is the incorrect one because it's negative, but it's like consistently incorrect. And then otherwise we're just the string. And again, this is the sort of stuff that we notice. However, even though we use the string, we don't use any of its Basilian member functions. We just use algorithms, right? We don't call string.find, we use our find algorithm. We don't call replace substring, we use our algorithms. Like strings are just ranges, so we just use algorithms. Similarly, we don't have a string view type, right? Instead, we've got span, which is like the generic, this is a subrange. It's a subrange of a contiguous thing. And so string arguments are not different from any subranges. So we don't use the string view, right? It's just a subrange into some other range. Like there's no difference between like a string view and a span, like it's both the same thing. And then for formatting, the de facto standard is like FNT. It's now part of the standard. And you sort of have like the placeholders there, and then you can also put in formatting characters. And so we've got like this embedded DSL in the string, and then some special functions to do like more advanced stuff. And then you specialize some traits to do like formatting support. And this sort of function eagerly creates a string. And we don't really do that at ThinkCell because strings are just ranges. And for example, format, we want to create a range of characters that begins with the answer is, and then has the number 42. And so we use a range algorithm for that. Concat, right? We give it a string, the answer is, and then we want to say 42 as a decimal. And this is a function that takes an int and it lazily returns a range of characters that is the decimal representation of that int, and then another string. Similarly, so we want to convert the MAC address into a padded hexadecimal number using transform, and then we want to join the range of ranges into a single one. And these are lazy range algorithms that are more generic than the format one. We don't have any DSL, we just have the functions that take some value and return like a character range of that thing. And adding formatting support just requires writing more of those functions, right? So we do have like strings with placeholders for like internationalizations. So we've got a function TC placeholders that sort of takes a string and then also optionally named arguments and do that. But we just use them for internationalization, and the string doesn't control any formatting. So when we want to say pi in there, like this just means the value of pi gets inserted in there. And then the caller needs to specify how statically, how is that converted, and not the translator of the internationalization string doesn't get to control the formatting. It's part of the code. And again, this is like our approach because we feel like strings are just ranges, so we don't need a special case formatting. It also means that it's really useful that concat is fast using generator ranges because we use concat a lot in our code base. Like we have C++ code that generates the website of our company, and this is essentially just like one big concat that generates HTML that is then takes a while to compile though. Similarly, files. So files are just ranges. So reading a file, we just take the file object, call for each, and this will give us each individual byte. And then writing, well, we can use append something to a file. And then you can just use any high-level algorithms on the range that you've just created. And again, this is also where it's really convenient that we've got this chunking, because we don't want to write each individual file character by character to the file. You just want to write chunks. And so this is just something our library offers. It has like a bunch more stuff. We've got enum reflection. I'm using macros because we don't have reflection. So for example, you can have all values, and this will arrange over all enum values, and so on. We've got specialized data structures, optional references, static vector, maps from enum to values. We've got JSON and XML parsers. I gave a talk about them at CPAPCon, a video gonna come online soon, so a bunch more. So again, we're hiring. So if you want to work with this library, you get frequent breaks while it compiles when you start working with it. We're hiring. It's open source, so you can find it there. Thank you.
Maybe if you have some extra questions to Jonathan, I can give you a mic and you can still ask them. And he has prizes.
Yeah, yeah.
So just raise your hand, I'll bring you a mic.
Yeah, elaborating a bit on the compile time performance question as well. There's also the question of like some aspects of developer experience, right? Where you like have too many wrappers, like too many tasks that are like are implemented as functions, right? That besides adding to the compile time performance issue, also makes debugging things harder, right? In some other ways. So.
Yeah, so we're getting compile times. A clean rebuild on my machine takes about 15 minutes of the entire code base, which isn't that bad. Like could be worse. No, like of the entire company product. So, and like we are starting to monitor, like I did some compile time optimizations in there, and when we switch to modules, it might help, and we use pre-compiled headers and so on. And yeah, so yeah, but like fundamentally, this is definitely a problem that we need to watch out for. Regarding debugging, yeah, we've got like pretty big stack traces in places. You can really scroll through them. But like we've got a bunch of the infrastructure, like debugging, not debugging tools, but like debugging utilities that make it easier. So this isn't really a problem, I would say.
Yeah, but you thought about compiler extensions, right? So like there's people working, like for example, take casts in general, like where STD moves, right? There's people in Clang right now, doing that kind of stuff as like a built-in.
So there are like facilities to help with I'm looking at that. For example, like move is a macro in our case, exactly for a similar reason. And then translating like tc invoke is also a macro. Even though like it calls like a bunch of functions internally because of compiler bug and Clang, whatever. But like the sort of like, I'm aware of the techniques we're looking at. Thank you. Yeah, so we are always using the latest one. So like as soon as like MSVC supports the feature and Clang supports the feature on Mac, they will start using it. So we're just always on the bleeding edge. I have like whatever's currently.
So you're not saying the latest standard, but actually the latest flag, because like before C++ 23 was released, you're using kind of like incomplete implementation.
Yeah. So we're using whatever our compiler supports. We start using it.
That's a bit strange, isn't it? I mean, I think if you want developing a library, you want to use it.
Yeah.
By what version of what standard they can use.
Yeah. So we're using the library internally as our main thing. And so like it's a problem if like yes, but
clients and things so also might be constrained by some.
Yeah, clients of the library would also be then similarly constrained, but like we don't want to be constrained internally just because we've open sourced it to then,
I understand.
Thank you for the presentation. The quick questions, as you showed before, you have optional of the reference, right?
Yes.
And we don't have it in standard library. So why do you think is that the case?
We don't have it in the standard library because people in the committee, there was a split between what should assignment do on an optional reference. Should it rebind to a new value or should it assign the reference? And there's like one obvious correct answer, but like 50% of the people are just wrong. So it's not. Yes.
And what was your choice?
But rebind. Yes. Yeah. Obviously.
Anything about reflection?
Yeah. So we do like the EDOM reflection using macros. So the mainly So we got like the classic enum to string reflection available using macros. Then we've got stuff to reflect. We've got like serialization stuff on like classes, but this isn't done. But this is like semi-automated, so you just have to give it a list of members, and then you can, for example, generate a hash out of it, and that sort of thing, right?
Using the pretty function.
No, we're not using the pretty. No, we're using boost preprocessor a lot to just give me a list of things and then do something for each thing. Yeah.
Let's get the example of the optional for a reference. What happens? I don't know if already happened. If the SQL adopts optional of reference, would you, roll back and adopt std or keep using yours?
Yes. So we, for example, we want like if there's something in the standard library that is like equivalent to our code, we will use the thing from the standard library. So like we recently migrated a bunch of like three-way comparison stuff to the standard one. With optional, like there is currently another round of proposals for like optional reference, and once that's adopted, we might consider switching over because, for example, the monadic operations, we would need them because we've got like the non-member ones, right? So we don't use a lot of the interface of the type because you do a bunch using non-members because they're more generic. With optional concretely, we've also got optimizations for optional of empty type, which isn't stored in the optional, so it just stores a bool, essentially. And then we can do some optimization with that. And particular with optional, because we have got a bunch of re-entrant code, due to the way the code base is structured, there is some technical details about the order in which the type is destructed that we need to have a guarantee, which the standard doesn't. So we probably have to stick with their own ones. But in general, I've recently thrown out a bunch of meta program stuff and replaced it with Boost MP11, for example. So we don't want to reinvent the wheel when we don't have to.
One more question. Is this library open to external contribution, or is it something only?
Yeah, so in principle, it would be open to external contribution. In practice, this is a bit tricky because right now we're not developing it on GitHub first, but we're developing it in the monorepo, and then in a couple of months, I copy-paste everything over to a single commit with the changes. I want to change that eventually over, so then we can do it like an open source first implementation. But if you want to contribute, just do a pull request, and I will. Well, like it's my problem essentially, right? Not yours.
I basically have two questions. First one is you explicitly mentioned 2 times that you have fancy code that can do optimization for deck copy pasting, like using memcopy. How do you do it? Because I'm curious. There is no API to expose it, right? The internal structure behind.
Yes, so we don't have like std deck, but we've got like a type in our code that is not quite std deck, but like the pattern of like it's like a linked list of contiguous ranges essentially, and then we can do the optimization. And we also use it with like a bunch of file stuff where we can just give me like a 1 kilobyte buffer of the file, and then we can.
So it's not actual std deck.
It's not actually a std deck. It's just the example.
And I have another question about one of the slides that you have. You have filter, and that takes range, like range that you pass by copy. Like, is it intentional? Because from what I remember, like you have views which usually take a pointer. Is it just to avoid dangling reference, or why is it? Like that?
So this might be like slide codes. So in practice, the standard ranges have the distinction between like a range and a view, and the view is like a cheaply copyable range thing. We don't have it. Instead, we say that if you give a range algorithm, that takes a range. If that is an L value reference or something like string view, so it will essentially like store span internally of the range. And if it's like an R value vector, for example, it will own it and solve it. So it's safe in that case. Then we also do a bunch of changes in place.
I have a question about the files as ranges. So how do you handle the file errors? Like, do you, whenever you iterate, in both ways, when you read like as a range and when you write into like from the range?
Yeah, we throw an exception. if it's never. What? No. Yeah, not with that API. Like we throw an exception, and because like again, like we're in the context of an GUI application, we throw an exception. So we've got like a handler that then gives the user a popper and says operation failed. Try again. So it's like a very convenient way. Like we don't need to worry that matter about errors. Just stop at the appropriate thing and pop up a message box.
Okay. More questions? Then maybe let's thank Jonathan first. So we'll have something like 15 minutes break, whatever is left from our half an hour. I think that's still enough. And I think, Jonathan, you have to find the people to reward with prizes. So just gather them somehow.
You can take something. Yeah. Then I have nice prizes. If you want, you can take something. You just asked you a question. I forgot one of you. You can take something. Yeah, sure. And then you too. You were asking during the talk, I think. Yeah. Oh, of course, you can also have one, and then go. Yeah. Okay. And then we've got more. Yeah, we've got stuff like just.
Yeah, I think Anna and Julia could help you. So if you just go outside through them, you'll grab your nice stuff.
Yeah.
And so 15 minutes break, and we're back here by 8:30 for the second talk. Thank you. So we had a nice talk from Jonathan previously. Thank you, ThinkCell, for bringing Jonathan here. And the second talk is from Dmitry. Dmitry is a team lead in our C-Line team. He's not going to talk about the C-Line to you, but if you have any questions afterwards, and I heard some praises for Nova here, so you can come after the talk and share your feedback if you wish. And also we have some prizes for the best questions, and because you stayed till that late, want to reward you, so we have some free licenses for our C++ tools. So just be engaged with the questions, and I guess that's it. That's your stage.
Yeah, hi everyone. It was completely accidental, but I think the two talks have some kind of nice synergy between them. So indeed, I work on C-Line ID, and I have a confession to make that I actually didn't program in C++ for like 8 years or something. So while I used to love doing what would be described here, I kind of out of the loop, probably. But still, I mean, the last few years I'm programming Google Docs and Slack. So, but still, we are talking to a lot of users. We kind of seeing plenty of diverse and very different C++ users with C++ projects. So I think I've seen enough to briefly talk about this stuff. And by the way, how many of you have experienced issues with slower C++ build times? Like ever? Yeah. Okay. Yeah, thanks. And how many of you have actually actively done something to combat this on the projects you're working on? Yeah, quite a few hands. So maybe, we'll see if you've done everything. So yeah, basically you're not alone. And in the C++ Foundation theory, it's like the second most annoying issue with C++, the build times. And yeah, why should we care? And it breaks down into different aspects. So like, of course, it's developer productivity, but again, it might be about clean builds or switching branches. It might be about incremental builds and like edit and compile cycles. It might about CI performance, so it might prevent you from doing tests, per comment test or something like that. And of course about costs. And any of these aspects might require different approaches. So some of the approaches will work for all of it. Some of it might have some drawbacks, and you might have to do compromises. Yeah, and before jumping into things, I also just very briefly will mention what we're actually talking about and how the C++ projects are usually built. So yeah, and again, why I'm talking about that, each of the stages might require different approaches, and making one of it faster might make other of it slower. So, yeah. So first thing first, the build system usually it's kind of CMake or something like that. It needs to detect changes, detect that something has changed in your project if it's an incremental build. Then when it's done, or maybe if there is a clean build, it maybe need to configure stuff. So you know the thing when it goes and asks if you have a compiler, if this compiler is C++ compiler, if it supports, it has printf function, if it has a printf function, if it has scanf function, so on. Yeah, this kind of thing. Then again, it calls the actual compilers, usually in parallel, hopefully. And yeah, if we're not talking about C++20 modules, we will, but later in the talk. So the preprocessor will join all the includes together. That's what we mostly care about here. And this basically means that all the includes are processed multiple times through the whole project build. Yeah. Then the front end parses all of it, does all kind of crazy stuff, does some optimizations, does template instantiations. Then the backend does optimizations or more of it, depends on the compiler. Codegen happens. Then also maybe the debugging for it generated, which also can be pretty expensive. And then a bunch of object files are linked together. So I will be trying to talk about how to speed up some of the things and how to measure some of the things. But probably before that, I will start with some easy solutions that probably doesn't require to measure anything and can be just applied universally and just try it out of the box. And yeah, probably for a lot of people, the first and last stop is here. So you just buy better PC and be done with it. Because like it's not like that expensive. It's expensive, but still, if you spend I don't know, 300 hours optimizing your build performance, you might consider and like gaining 50% of it, you might consider just buying a Threadripper workstation and gain the same 50% absolutely for free. And then you can play games. Then you can everything is faster and just. Another like a common advice we often see from the users, it's not really obvious, but also deal with your antivirus software. So like Windows Defender is always on, and unless you're using this kind of new thing from Microsoft, it really affects stuff, both the tooling performance and the compiler performance. It's not, I'm not joking, a lot of people has that enabled for the builds. And then, yeah, everything is mostly CPU bound, assuming you have enough RAM. So yeah, get a better PC and enough RAM. So nowadays, like RAM disk usually not happens that much, assuming you're CPU bound. And yeah, at the same thing, like in the same bucket of throwing money into it goes all the cloud development things. So where you develop on a remote beefy workstation, I'm not going to talk about it because it's like really employer dependent or vendor dependent or yeah, if you can do that, you know better than me what you can do with it. Yeah, and then the next obvious thing is just use a better linker. So you know there are multiple linkers out there, and on Linux, the default one is the LD on Linux and the Linux-like distributions on Windows, and it's also the slowest one by far. So all of these are kind of drop-in replacement for each other. Like the Gold is also from the GNU toolchain, but it only supports ELF. So if you want something else than ELF, you probably know better than me what you want to do. Yeah, and the LLD is the one from LLVM, and the toolchain and the mold is a new shiny parallelized thing that is developed by the same person that who initially developed LLD, I believe. So it gets some credibility, and yeah, they recently switched license to be for a more permissive one. So yeah, if like we will later find out how to detect if you are bound by linker, but you might want, if you on Linux, if you did nothing about it, the chances are you are bound by linker, so you can just try it. Yeah, and then again, thanks Captain Obvious, but you can try another compiler. Yeah, I mean, two things why I'm talking about that. One thing is that they used to be a common knowledge that Clang is faster than GCC. I believe it's not the case anymore. Well, when Clang catch up in features, for some unexpected reason, they dropped in speed, so they're kind of comparable right now. So yeah, but just switching compiler might give you some gains. And also, if you want to diagnose something about your code base, and if you want to apply some of the tools I'm going to be talking next, you probably want to make sure your project can be built with Clang, because, well, a lot of the tools are Clang-based. So even you, for example, try Clang CL instead of Visual Studio Compiler, and even if it doesn't end up in better performance, you just you are now able to run tools. Yeah, and again, I'm listed the obvious ones, and like replacing MS Visual Studio with GCP might be a bit more problematic than that. Yeah, another thing. So again, if you're using CMake, well, you know that CMake is a meta build system, and it generates stuff. And by default, I believe it still generates make files. And Ninja is kind of a alternative to make files, initially created for building Chromium. For some reason, a lot of things for build speeds are initially created for Chromium. Yeah, so it's fast, it's simple, it doesn't have a lot of features, it's not flexible, but that's why it's fast. But the main thing it optimizes the incremental build speed, so it improves the edit and compile cycle, and it usually doesn't help with clean rebuilds and stuff like that. But still, again, as the CMake default is not Ninja, that's probably something you want to try. Also, while Ninja is usually intended to be generated, it's like surprisingly pleasant to write by hand if your project is simple enough, and if you don't care about cross-platform and supporting multiple compilers, just write in Ninja by hand to compile your code, or maybe to just run any kinds of tools in parallel with dependencies between them. It's kind of surprisingly pleasant and so straightforward. Yeah, and then the next thing, it's kind of low effort, but still it's a bit more effort than before. It's any kind of caching and distributing compilation. And most of the things works in a way of compiler wrappers. Well, not always, but usually. So your build system calls build system thing, it calls a compiler, but actually it's not a compiler, but a thing that does some funky stuff. So in the caching side, the most famous one is CC cache. It's chances are it's installed on your system or it's available in the package manager. And again, but it has kind of limited usability because it doesn't improve full rebuilds unless you have already built the thing at some point. So it improves rebuilds when you switch branches, because, well, it's a cache. It needs to get data from somewhere. It improves things if you have multiple working copies spread somewhere. Improves things if you often do clean and rebuild for some reason unrelated to actually building stuff. And also it has this feature that the cache can be distributed, so it can kind of act like a distributed build, but yeah, it's still sort of a cache. But generally, if there is nothing to get the data from, so if you build it, you're working alone, it will probably make your overall build performance slightly worse, because, well, it's not completely free. Then there are these things about distributed building. It's when you think that your colleague has too powerful computer and you want to use it instead of yours, you can install like a tool on your colleague's computer and build it there. So yeah, the Incredibuild tool is mostly for Visual Studio, I believe, at least initially. The ICC is the tool from Mozilla. It also supports Rust, I think. Yeah, and the DCT is the original Linux thing. Yeah, and then there is another tool from Mozilla. I have no idea why it's different from ICC, and I believe it also supports Rust, and it's like both caching and distributing thing called STC cache. Like we're using the last one, like internally, it kind of works okay-ish for building some of our stuff. Yeah, and that's all the easy and immediate things that you can apply blindly that I know of. And then if it doesn't help or it's not applicable to you, you probably want to do the same thing that you always do when something is slow. You need to profile it. And let's talk about how can you measure some build-related things. One of the more niche ones is that, well, you know, sometimes people complain that the make configuration and generation phase runs slow. It's not about the build, it's about the configuration step. Again, actually, CMake has this thing with the built-in profiler, which can output the data. And yeah, it can output the data in this format called, like in the format for Chrome tracing tool. We'll also see a lot of usages of this tool as well. Well, basically, you can go to your Chrome-based browser, go to Chrome tracing, and you can open some JSONs there. And also there are competing UIs for that. But anyway, it's somewhat niche because not everyone suffers from that, but if you suffer from that, you know that. So there is this tool. And also, yeah, I believe the Selenium IDE has some experimental support of showing the same thing. But let's go to the real stuff. So now let's imagine we're using Ninja, and we actually want to understand why our build is taking so long. And luckily, Ninja saves everything it does in so-called Ninja log file. Again, it's pretty straightforward. It's just like the event and timestamps. But still, there are a bunch of tools. For example, this one that parses Ninja log and visualizes it in the same Chrome tracing JSON. So this is like, because C++ builds are generally can be highly parallel. So how they call it, embarrassingly parallel. So that's how like normally the build should look like. And if it doesn't look like that, there might be room for improvement. For example, if you see that all your cores are idling, waiting for some task to finish, it might happen in your project. It's some just you can look for that. And yeah, of course, like you can eyeball the thing and look for bigger things and slower files, because, well, usually it's either compile jobs or link jobs. Yeah, so, but you then you find this longer file, and what can you do with that? And again, there are easy solutions. A lot of people probably aware of. You can just dump include tree. And again, often, if you never profiled your builds, if you never look into it, it very well might be enough to find some interesting results, because you can just eyeball the results for surprising dependencies. For example, like back when I was developing in C++, I was kind of doing this kind of thing, and someone used boost lambda instead of something else in some rarely used function that was put in the commonly used header, and just like by removing it, the overall build times improved like 20% or something. So yeah, if nobody ever looked for this thing in your project, it can help. Yeah, but there are also better ways to approach that. Since not that long ago, someone contributed a time trace flag to Clang. So if you have a file that can build with Clang, you can pass it. You can pass this flag to Clang, and it will also produce this thing in Chrome tracing format. It will show both front end and back end. For the front end, it will show the files it goes into. For the back end, well, it shows what it does. So, for example, you can see if you're running optimizations you don't need for if you're just doing an editing compile cycles, and you can turn off the optimization. Or if it's front end, you can inspect the specific files and specific templates that are instantiated. Yeah, it's pretty useful, but still you need to inspect files one by one and again eyeball it and do some guessing. Then there is further tools. There is this Clang build analyzer tool, again available on GitHub. Luckily, someone wrote it. It basically takes all these outputs from Clang time trace for the whole project, and it does some aggregated reports on that. So it can show files that took longer, which is kind of trivial, but it also can show expensive templates and expensive headers and pass and various passes to how these expensive headers are included. So yeah, probably the latter is the most useful thing, because again, when I was preparing to this talk, I took a project I was not familiar with. I just ran this tool, shuffle the headers a bit, and literally in 10 minutes, I got, I believe, like 10% improvement on a project I know nothing about. So, yeah, there might be a bunch of low-hanging fruits there. And for the templates, it may be not that easy. It may be like for things like Jonathan was talking about, like you can, if you're developing template-heavy library, you might look into things that can be optimized just for compile speeds and build times. Yeah. If you're working with Visual Studio, though, there is something like that. So Microsoft also introduced that in their compiler. It's done differently. It's done on top of the Windows event trace infrastructure. There is an SDK to access that, and yeah, and then there is a sample application that generates a similarly looking time trace. Yeah, I believe it's a little less elaborate, but it still can be used similarly. Yeah, and then if you all you have is GCC, you're a bit out of luck, because while it has some tools, it feels like they're mostly targeted for GCC developers, not the GCC users. So yeah, you can. It's useful when you're optimizing like optimization passes in GCC, but it's less useful when you actually want to understand what's happening with your projects. So that's about the ways you can profile and see what's going on. Now about how to make it faster. And generally, the approach to how to make it faster, if we are not talking about the easy ones before, is just to reduce the amount of code you're compiling. Yeah, and the straightforward thing is the precompiled headers. So what is it? Is some kind of compiler data structure, abstract syntax tree, or something else. It's serialized to disk usually, and then it's used instead of reparsing the headers. And yeah, the main question here is what do you put in the precompiled headers? And there is no easy answer, because if you put too much, you might be suffering because every change would be a full rebuild. Also, if you put too much, the memory pressure will increase on the compiler, and you might suffer. You might get out of memory because like these things might be huge. If you put too little, it might be too little, and yeah, they're not immediately free, so they're not exactly free, and it's kind of a trial and error approach. Luckily, CMake has the modern CMake has this thing, so you can do it straightforward and cross-platform. So it's somewhat easy to play with right now. Yeah, and another thing is Unity builds. Also, they're called Jumbo builds. Also, they're called amalgamated builds. So what does it mean? You take a few translation units and you basically include them together one by one and compile it as a single translation unit. And it helps in two ways. First, obviously, it's reuse headers because, well, thanks to the header guards, the headers are included in less translation units. And also, it helps with template instantiations because templates are instantiated once per translation unit. And, well, you have, and the same instantiation can be reused across different translation units. By the way, slightly off topic, but there was a project called ZepCC. It was a project on top of Clang compiler that does the same but without Jumbo builds about instantiations. It cached instantiations into some kind of compiler server and served it instead of redoing it. But yeah, for some reason, and it didn't really took off and kind of died down. That said, it was kind of an interesting project. Yeah, and that's kind of dangerous because, well, all your statics are not so static anymore. All your anonymous namespaces also not that anonymous, and it can break compilation. It also can introduce very subtle bugs because C++ is dependent on order of things. Yeah, and again, modern CMake has a way to offers a way to play with it, somewhat easy to group some files into Unity builds. So at least somewhat easy to try. And then while you can just inspect the results of various tools I've described, just eyeball it, there is also various things that help you with that. The most famous one is probably the include what you use tool. It's complex and it's powerful. Some consider it complicated or not stable, but still it can it finds unused headers. It can enforce some things about headers and can introduce forward declarations for you, or at least offer you to do that. Yeah. On the other side of the spectrum is C-Lions and C# unused include inspection. So we are trying to make it conservative. So we are battling false positives, but allowing some false negatives. And then again, there is this Clang tidy check. It's introduced not long ago about include cleaner. Well, it's include what you use, but way easier. It's very opinionated. So if you run it on your existing project, it likely will give you thousands of results. But if you start with it, you can you might be getting better results by just constantly making sure it doesn't trigger. Also, again, a bit of shameless plug. So the ReSharper C++ has this tool that shows the contribution of each included header file in Visual Studio. I believe the Visual Studio itself has something similar. Yeah. Yeah. The next thing, well, it's again kind of well-known thing is that you want to use forward declarations. And here I'm showing this website called C++ Compile Health. While slightly outdated, it shows nicely the impact of various standard headers and the impact of various well-known libraries. So yeah, you probably all of you probably know that there is this forward declaration for iOS streams, and this is how it can affect the build times when this header is included or not. And also, well, again, you can do it by yourself. You can introduce this kind of header by yourself, but also you, if you care about these things, you might be considering build times when you're choosing dependencies. For example, here are the three famous JSON libraries, and you can see that some of them are expensive. Some of them are even more expensive, but have forward declaration header. And like the rapid JSON is also kind of expensive, but it can be included. Only specific things can be included. So yeah, if you don't have any other requirements, so like you can choose your libraries based on your build times. And now I'm going into this kind of territory. It's either unconventional things or either things that are hard to do, or just random tips and tricks I wasn't able to put anywhere else. And again, first thing is you are building with Clang, and you have your specific project. You can build Clang with profile guided optimization and gain extra build speed. Actually, again, for C-Line, we kind of doing this with our fork of Clang DY bundling. So just rebuilding it using profile guide. By the way, what's profile guide optimization? You build your project once, then you run it on some workload under profiler, collect the profiling data, and then feed the profiling data to optimizers to optimize it further. And we experienced about 10 to 20% performance gain when we just built Clang using profiling data collected on its own tests. And if you have just your project to compile, and that's exactly the workload you will be using it for, you can collect profiling data from that. And people in the internet claim that it's up to 30% gain. I honestly didn't check it, but I tend to believe it. And LVM even has a special segment on how to do it. It's somewhat straightforward. Next thing is kind of lesser known, but again, often the debugging for generation is expensive. And by default, you usually have two options to either generate it or not. But a bit less known thing is that you can generate line table debug info. This way, you will get stack traces. You will be able to set breakpoints and steps through your code, but you won't be able to expect variables. And if that's an acceptable compromise for you, it might help a lot. For example, if you work on Clang compiler, it like saves, I don't know, it helps tremendously from my experience. I believe CMake doesn't have a built-in thing to do that. You might need to do some careful compiler flag jungling with CMake, but yeah, it often helps. Another kind of lesser known feature, and now it's feature of Ninja, is that Ninja has the concept of pools. So basically, it can schedule different types of tasks to have different maximum amount of parallelism. And CMake has two kind of pools for Ninja. You can control compile a link pool separately. And why it's important? Because like most of the times, the compile jobs are CPU bound, but often the link jobs are memory bound. So if you have a lot of static libraries to link together, and if you do it all at once, you might well run out of memory and suffer a great performance hit. So it's often a good idea, well, after measuring, to keep the link parallelism down, and CMake together with Ninja offers a way to do that. Yeah, then another somewhat controversial thing is, well, CMake is not the only one meta build system out there. Yeah, and Google, again for Chromium for some reason, created another build system called GN, which is short for Generator for Ninja. And it's basically the total opposite to CMake. So they take all the CMake design decision, do it in an opposite way. So it's no convention, very little auto configuration, it's kind of difficult to use. It's just Ninja backend, but it offers. They claim that it offers better incremental compile and edit and compile speeds, and I kind of tend to agree with that. But yeah, I don't think there are a lot of projects out there that has GN as a build system. For some of them, Google supports that. Again, for LVM, Google supports it alongside CMake, but still, yeah, it's kind of esoteric thing. Another build system, also completely different one, is Bazel, and it's currently being more and more popular because it works well with giant code base and monorepos. And while the build system itself is slow and clunky, and is written in Java, and it has some weird dialect of Python as a configuration language, because it focused on geometric and reproduced builds, all things around caching, build results, and reusing it are kind of straightforward. So they have the remote caches and just the compilation caches built in, so you don't need an extra compiler wrapper. So maybe if you have a giant code base and if you have a lot of people working into similar environments, maybe Bazel is a way to go for new projects. Yeah, and that was kind of my take on various tips and tricks. And now the elephant in the room is, what about modules? They claim to save us from the slow build times. And well, the answer is kind of, it depends. Now, first let's see on the state of C++20 modules. I believe it's still up to date. It's kind of doesn't work for every compiler and every build system. It only recently got out of the experimental state with CMake. It works for Visual Studio because, well, they're kind of pushing the whole idea to C++. It still doesn't work with upstream GCC. Clang still misses a bunch of important features, but, well, I believe right now it's way more production ready than it was 2 years ago. Hopefully they will soon be just completely production ready. And yeah, by the way, I'm not going to talk about modules a lot, but in very generally, together with the object file, you generate, the compiler generates a so-called binary module interface that's consumed instead of header when you're compiling something that depends on the module. So it's kind of a precompiled headers on steroids. Yeah, and how does it interact with build times? It actually depends. So, as I said, with generally C++ is embarrassingly parallel to build, and it's not true with modules, because now the order of the build, how do you need to build the files, it depends on the source code. So you need to go through the files, figure out the dependencies between them, and only then you can go ahead and build them. So it's less parallelism. It's difficult to implement and build systems. So again, CMake just put it out of the experimental state maybe a few months ago, or even a few weeks ago. So basically, and I actually don't know the question whether modules actually make your build times faster or not. And that's actually a question. If anyone has real-world examples, I would be really interested to hear it, because I'm not aware of real-world migration of examples of existing code-base to modules, whether it be proper modules or header units. I've seen reports on the internet that some type projects show like moderate improvements from up to 50% or something like that. And the actual results probably depends on your source code. If you have a lot of like a giant code base, if you have a lot of complicated headers with a lot of inline code, a lot of templates, you probably will end up with more major speed up. But if your project is more like a usual C project with small headers and with a lot of code inside C or inside C++ files, it probably the lack of parallelism will probably bite you, and you might even be you might even get some slowdown with modules. Yeah.
Why is the lack of parallelism? Is there a reason?
Yeah, I mean, without modules, imagine you have two CPP files and a bunch of headers included there. You can just take both of them and compile it independently. And well, if you have a large project and you maybe have 1,000 header files and 1,000 source files, you can just take 1,000 source files and compile them all in parallel. Then with modules, it's not the case because all your headers now became modules. And now you can just take the source files and compile them right away. You need to, before compiling a source file, you need to compile all the modules it requires. So first you need some way to process them. And then there is a graph that you need to traverse, and it might have some bottlenecks. So yeah, you won't be doing extra work, but if this extra work was not that expensive, for example, in case of small headers with just pre-declarations, it might even be slower. Yeah.
Data point for you about using your module. So it's not exactly the same thing because client has two kinds of source module, right? It has C++ training modules, also has an older client modules thing. It's different. But Google was heavily invested in that. Gave numerous talks. They had advantages during their model repo with that. But they're using that
yeah. Like I know at least two definite improvements with modules. It's internal Google code base. Well, they have this, like as you said correctly a long time ago, it's usually called Clang modules. And Microsoft, they definitely they claim that they migrated to modules in some of their projects a long time ago, and they claim they have improvements. But yeah, I would be really interested to see any kind of available examples. Yeah.
My real world example, if you just grade to Clang 17 as new standard, like it allows all STL headers to be converted from includes to module. So it already just by doing this, or it is like 20% in my build, just because we're not really careful with iOS forward versus iOS streams. So probably that one alone and a bunch of other like C++ headers, just by pre-compiling them, they give it like just by this, like even no code base change, but just by allowing it gives significant improvement.
Yeah. So you're saying it's 20% without.
We didn't migrate code base.
Okay.
So
yeah.
it's only like it basically it uses STL as a module,
sure.
right? Like,
yeah.
The internal code base is not, so it's like in that case, 20% in our case.
Yeah. Yeah. Thanks. And yeah, like the code, the things like in STL, especially in expensive STL headers, it's probably the perfect example of things that can be migrated to module because, well, they're used everywhere, they're expensive, they're complicated, and so yeah. By the way, I was looking for it hard, but I failed to find this slide from one of the Google presentations about all the things. And basically they claim, and it kind of makes sense, that when the project is growing, the amount of, like the size of an average translation unit also grows, because like people are not disciplined enough to keep everything contained. So basically the overall amount of code you need to compile grows faster than linearly with like the amount of lines of code in your code base. So the bigger your project is, the probably the more impactful modules are, because like you have these just huge translation units with a lot of wasted, a lot of same headers included over and over. So yeah. Yeah, and generally, I hope that it will improve compile times. I would bet like 2 times improvement overall would be a good thing, but probably not more. Just taking some numbers out of thin air. Yeah, and that's actually all from my side. Thank you. There are some useful links about that. I will maybe post it somewhere if there would be a place. So yeah, thank you very much.
And if you have questions, I have Mike.
Question.
So one thing you didn't mention, but it's very important nowadays. Talk about LTO. Like if you have anything interesting to say about that, like very few seconds, I guess. Question time.
Yeah, well, if we're talking about build times, so I probably have the very trivial thing to say about LTO. If your link times are slow, disable LTO. Yeah, and you can figure this out by looking at the data. But yeah.
But there's like things you can do about improving LTO. Like for example, in client you have thin LTO, full LTO, and like some other customizations you can do about that.
Yeah, thanks. Indeed.
Well, first of all, thank you for your presentation. You stated on a slide about unused includes that it was quite difficult and your tool is quite conservative still in determining if an include is needed or not. Can you briefly explain why and if a module can help there?
Yeah, so I'm probably not ready to answer about modules. It can help, but yeah, let's talk about the challenges. And yeah, basically the challenges are the main challenges is that you might say it's somewhat straightforward. So if you use some symbol inside the code base, it should be the include should be in your include list, and if you don't use it, it shouldn't be there. There are some exceptions. A lot of libraries, including standard libraries, use some umbrella headers. So you include from Boost, you include you can include specific parts of Boost, or you can include some bigger parts of Boost, and both of it is considered valid. You like the tool probably can just say you don't want this and you want another thing instead. Another thing is that the difficult thing about unused include is that, well, you can't really say if the same include is included transitively through some other stuff. You can't 100% say if it's actually intended to be included there as well or not. Well, that's because umbrella headers. And also, you can't really say if some header is intended to be like implementation detail or not. So you can't always offer to include a more specific one without knowing if the library author allowed the user to access the more specific one. And yeah, hopefully it would the models will help a bit with that, because with models you can be more explicit what's visible and what's not. So you don't need to see all the things from top to bottom through the preprocessor, but yeah, hopefully it would help.
Thank you.
Thank you very much for your presentation. I'm thinking of ways to improve performance by changing your habits in programming. Like, would you suggest lowering the warning level so that the code analysis is less time consuming, or is that really minimal what you gain from warning level lowering?
Usually it's not the case. Usually, like at least the warning that compilers produce nowadays, they're usually produced on the way as they parse things alongside the and compared to what they need to do to actually do parsing and semantic analysis, the warnings are not really expensive. there are a few, there are some checks, for example, in Cloud Tidy or in Clank Analyzer, there are expensive checks, but I believe, well, it's not part of the build. So it's, unless you run your static analysis tools as a part of the build, it doesn't matter. Yeah, and like for the compilers, I'm not yet aware. Well, sometimes it might happen if you output like gigabytes of errors. It's like as gigabytes of warnings, it might be different, but generally I'm not aware of any specific warnings. I haven't seen it that actually expensive compared to the generally compiling the code.
And then, for instance, to use pragma ones instead of include guards.
Yeah, well, all the modern compilers are smart enough to understand that include guards, what include guards do, and then to do the right thing.
Shouldn't. Okay. Thank you.
Thank you for the presentation. I was thinking, is it possible for some of this technique to be harmful for low-performing PCs, and be beneficial for 1 terabyte RAM as our previous presentation? So, yeah.
Yeah, sure. Like for example, the precompiled header, they generally increase the memory footprint of the whole compilation. So, like putting a lot of stuff into precompiled header might help with some more performant PCs and making worse on some less performant ones. Probably the same for Unity builds as well. So if you just run out of memory, it's terrible, and it's usually the worst thing you can do with your performance is to run out of RAM, and well, there are multiple ways to get there.
One of the things that you haven't mentioned is, for example, moving your host OS to a different OS. For example, builds on Windows using GCC-based toolchains tend to be very slow. So, for example, for our embedded projects, a simple compilation could take like 18 seconds on Windows. Moving to the same compiler on a Linux-based system through, for example, WSL2 would take it down from 18 to like 8 seconds. So that might also be worth exploring.
Yeah, thanks. Actually, I think I wanted to talk about it in some slide, but forgot it. Yeah, and that's indeed true. And WSL is also known, not really known for the top-notch performance. And also it depends on where the sources are the sources inside the WSL or other sources in the host system. And yeah, generally also like the Windows builds are the slowest ones from my experience. Then the Linux are the fastest ones, but the builds on macOS are more user-friendly in a way that, like, on the most distributions I've seen, they behave very aggressively around the memory usage. So, and like the system allocation usage. So you get faster builds, but everything like freezes. So yeah, indeed, maybe migrating to Linux if you can afford it, it might save you some time.
But on Windows, the file system performance is the critical thing, where one of the things you mentioned, the antivirus problems worse there. So there's a difference like in WSL as well, where you have WSL 1, like if you're doing anything on that, you're going through the Windows file system. But if you're using WSL 2, that's like using virtualization. So if you're using Linux file system within WSL2 and not your Windows through WSL2, that tends to be almost as fast as building on Windows.
Yeah, thanks. Yeah, and also I think that like nobody uses WSL1 anymore, like generally. Yeah, and it was really not really known by the best performance around file system. But yeah, I think that a lot of tasks are CPU bound, so it's not really affected by the Windows file system performance. Yeah.
Yeah, more questions? Okay, so Dima, you have the same task as Jonathan. You have to select some winners, and you can just give them their licenses. That would be easier for you.
Yeah, I could pretend that I remembered everyone, but I won't. So could you please, if you ask the questions like lately, could you please just come here and we'll provide you some licenses.
Yeah, okay. And let's thank Dima, and thank you for coming today. Yeah, and so don't forget to grab your prizes and hope to see you soon.